Welcome, dear friend, to Dreamtime Science. Imagine yourself amidst shelves of ancient books, their spines worn soft under the gentle glow of a bedside lamp. The night outside stretches quietly, stars whispering old secrets through the window. Here, in this calm nook, we invite you to drift gently into stories wrapped in tranquility and wonder. If this moment feels right, a quiet tap of the like button or a soft word shared in the comments about where you listen from would mean the world. Let yourself settle now, adjust your pillow just so, breathe in slow, even rhythms. Together we will wander softly through the twilight realms of knowledge, letting curiosity soothe the mind while sleep tiptoes closer. Whenever you are ready, let your journey begin as we turn the page together. The meter began as a fraction of the Earth itself, a line drawn across continents by Delambre and Méchain, their compasses and telescopes aligned with the stars. Meanwhile, the kilogram once floated on the edge of a scientific debate, tied to water's elusive density. Even Gödel's proof hinted at the limits of measurement, a quiet echo in the system's design. Yet the metric world thrives on simplicity, decimal steps that turn millimeters into kilometers with ease. The lecture is about to begin. If this peaceful blend of science and serenity helps ease your evening, consider joining our community of gentle learners. Share your favorite moment of scientific awe in the comments. Let's prepare for tonight's journey. Find your most comfortable position, let tension float away from your body, and take 3 slow, peaceful breaths. Night settles in a hush of pale light, silvering the corners of a quiet room. The world outside is washed in calm, motionless, except for the faintest movement of air, the gentle shifting of leaves against the window. Inside, a table stands, its surface empty, but for a single slender rod of metal, unadorned, unmarked, but heavy with purpose. The room is neither grand nor cluttered, more a space for reflection than for labor. Shadows rest in the corners, and the air holds the faint memory of old paper and polished brass. Here, in this stillness, the topic of our story finds its first quiet breath, the pursuit of a common language for the world's measurements, the birth and spread of the metric system. For centuries, the world's distances, weights, and volumes were measured in a tangle of local tongues, feet and stones, cubits and gallons, each rooted in the habits of a region, the length of a king's arm, the fullness of a merchant's vessel. To measure was to trust, and to trust was to know the customs of your neighbors. Yet as the world grew wider and more entangled, trade stretching across seas, science reaching for the invisible, this patchwork of standards became a labyrinth in its own right, a maze of conversions and confusion in which the meaning of a single length or weight could shift with every border crossed. In the late 18th century, as the Age of Enlightenment swept across Europe, a new idea began to stir. It was a time when reason was prized above tradition, and when the dream of a universal order seemed almost within reach. In the salons of Paris and the academies of science, voices rose in favor of clarity and unity, a system of measurement that would belong to no single king or country, but to all people everywhere. The metric system was conceived not as a tool of rulers, but as a gift to all who measured, weighed, or counted. The first of these new standards was the meter. Its creators, among them the French astronomer Jean-Baptiste Delambre and the mathematician Pierre Méchain, sought a definition that would be both precise and democratic, untethered from the whim of any living sovereign. Their solution was elegant in its ambition. The meter would be 1/10,000,000th of the distance from the equator to the North Pole, measured along the meridian that passes through Paris. In theory, every meter on Earth would then be the same, a slice of the globe itself, an invitation to unity written in the language of nature. To bring this vision to life, Delambre and Méchain embarked on a journey both arduous and quietly heroic. For years they travelled the length of France, carrying delicate instruments through fields, forests and towns, measuring the land with astronomical precision. Their task was both scientific and symbolic, to bind the world's measurements, not to the body of a king, but to the shape of the planet itself. The rod of platinum that eventually rested on that table, its length exactly 1 meter, was the culmination of their labour, a physical embodiment of a new idea. The metric system did not stop at length. It flowered into a family of units, each related by powers of 10, simple, scalable, endlessly adaptable. The gram was born as 1,000th of a kilogram, the kilogram itself defined by a block of platinum kept in a vault near Paris. The litre, the second, the ampere, each found its place in the growing constellation of measures, each linked to the others by a logic as clean and regular as the ticking of a clock. The beauty of the metric system lies in its simplicity. Instead of the elaborate arithmetic required to convert feet to inches or pounds to ounces, the metric system asks only that you move a decimal point. A kilometre is 1,000 metres, a milligram is 1,000th of a gram. The system breathes in patterns of 10, a rhythm that echoes the structure of our counting and of the very numbers themselves. For scientists, engineers, and schoolchildren alike, this clarity is more than convenience. It is a liberation from confusion, a thread that leads through the labyrinth of the physical world. But the journey from vision to universal adoption was neither swift nor without resistance. Old habits, like old measurements, lingered. In many countries, customary units held on tenaciously, woven into language and tradition. Yet over the centuries, the metric system's logic proved persuasive. Nation after nation adopted it, first in Europe, then across the globe. Each conversion a quiet affirmation of a shared reality, a willingness to measure the world in common terms. If you imagine the world as a vast tapestry, woven from the threads of oceans, continents and cultures, the metric system is a kind of golden thread, running quietly through the weave, linking distant places with a single, unbroken measure. Even where other systems linger, the metric remains the language of science, the backbone of international trade, the grammar in which the universe's laws are written. Yet for all its reach and utility, the metric system's story is not only one of numbers and rules. It is at heart a story about making sense of complexity, a search for order in a world that often resists simplification. Here, the tale of the labyrinth finds its place. In the myths of ancient Greece, the labyrinth was a bewildering maze built to contain the Minotaur, its paths so tangled that none who entered could find the way out unaided. The hero Theseus, sent into its shadowy corridors, did not rely on strength alone. Instead, he carried with him a simple ball of thread, a gift from Ariadne, unspooling it behind him as he walked. With this slender guide, he could trace his path through the twisting passageways, finding his way back to the sunlit world outside. The labyrinth is an apt metaphor for the state of measurement before the metric system, a confusion of paths, each leading to its own dead end, difficult to navigate and easy to lose one's way. The metric system, in this telling, is the guiding thread, not a weapon or a wall, but a means to find coherence amid confusion, to move from darkness into clarity, step by measured step. Consider for a moment the everyday miracle of this simplicity. To measure the length of a river, the height of a mountain, or the mass of a newly discovered element, one need only count in thousands or hundredths, each step predictable, each conversion a matter of moving the decimal. In the laboratories where new elements are weighed, in hospitals where medicines are dosed, in spacecraft where distances are calculated to the nearest meter, this quiet regularity is everywhere at work. The world's complexity remains, but our means of describing it become, in a small way, less daunting. The adoption of the metric system was not merely a technical change, it was a cultural shift. Measurement, once the province of guilds and local authorities, became a public, shared endeavor. The standards were published, the rules made plain. It was no longer necessary to appeal to the memory of a king's arm or the caprice of a market town. Instead, anyone with a meter stick or a balance could reproduce the same results anywhere on Earth. In this way, the metric system became a kind of quiet democratization, a promise that the world's truths were available to all who cared to look. There is something almost poetic in the way the meter was first defined, not by the artifacts of power or the accidents of geography, but by the very shape of the world itself. The planet, spinning calmly in space, becomes the ruler by which all things are measured. The air you breathe, the water you drink, the distance between stars, all can be rendered in the same language, the same gentle rhythm of tens and hundreds, scaling up and down with the needs of the moment. In the years that followed Delambre and Méchain's journey, the metric system was refined and extended, its definitions sharpened by advances in science. As the precision of measurement grew in the cool, ordered laboratories of the 19th and 20th centuries, the original meter bar was replaced by new standards, first by wavelengths of light, then by the speed of light itself, making the meter not a rod of platinum, but the distance travelled by light in a fraction of a second. The kilogram, too, would eventually be redefined, no longer tied to a single artifact, but to the unchanging constants of nature. Yet the spirit of the original vision endures. The metric system's elegance lies not just in its decimal structure, but in its rootedness in the physical universe. Each unit is an invitation to see the world as something measurable, comprehensible, and shared. To measure in meters and kilograms is, in a sense, to participate in a centuries-old conversation, a quiet agreement that, despite our differences, we can find common ground in the way we reckon the world. When you pour a liter of water into a glass, measure your height in centimeters, or watch a rocket's altitude climb by kilometers, you are engaging in this act of unity. The numbers may be small or vast, but the underlying structure is always the same, always familiar. This regularity gives not only convenience, but also a kind of comfort, an anchor in a world of change. In classrooms on every continent, children learn to count in tens, to convert grams to kilograms and milliliters to liters. The logic becomes second nature, a framework so unobtrusive that it often goes unnoticed. Yet this unnoticed simplicity is itself a triumph, the result of generations of effort, of journeys across fields and mountains, of debates and refinements, all in the service of making the world just a little easier to describe. The labyrinth is never fully banished. The world remains complex, full of twists and unexpected turns. But the thread endures, running quietly through our days, marking each step with a confidence born of shared understanding. The metric system is not a final answer, but a way to ask questions more clearly, to find our place in the maze, and to move forward with a sense of direction. As the quiet gathers in the corners of the room, and the last glimmer of light touches the metal rod on the table, the story of the metric system settles into the hush. Its origins are woven from ambition and patience, its logic as simple as the counting of breaths, its reach as wide as the turning earth. What began as a journey through fields and forests guided by the stars has become a path that anyone can follow, a thread through the labyrinth, leading not to the center, but to a world where distances and weights are shared, and the act of measuring is, quietly, an act of unity. And so, in this stillness, you carry with you the beginnings of an idea, that the world, in all its complexity, can be described with a handful of simple measures, meters and kilograms, threads and paths, each a promise of clarity waiting to be traced. In the hush of a late autumn evening, the scene shifts to the banks of a slow-moving river, somewhere between fields and forest, where the ground is soft underfoot and the air carries the scent of damp soil and cooling leaves. The river does not rush, nor does it trickle. It glides, indifferent to the boundaries that humans have drawn upon the land. Here, the world feels measured not in frantic seconds, but in the gentle accumulation of moments, a drifting reed, a ripple, the slow turn of dusk into night. Along the water's edge, scattered stones lie half buried in silt. Some are flat and smooth, perfect for skipping, others knobbly and resistant, shaped by the elements over years untold. There is a serenity here, but also a kind of order. Each stone, each eddy, each curve of the riverbank, arranged not by human hand, but by the universal laws of erosion and sediment. And yet, as you listen to the soft lap of water, you might sense another, subtler pattern, the way the mind, even in repose, begins to count. Steps from the path to the shore, the span of a stride, the time it takes for a leaf to drift from one bank to the other. Measurement, it seems, is as much a habit of thought as of tool. It is in a setting like this, neither laboratory nor marketplace, but quietly between, the structure of the metric system reveals its deeper elegance. The Enlightenment's dream was not just to replace muddle with clarity, but to create a language as clean and regular as the river's flow, a system where every part could be translated into any other by a simple, familiar gesture, the movement of the decimal point. At the heart of the metric system is this promise of seamless transition. To move from millimeter to centimeter, from meter to kilometer, is to slide effortlessly along a chain of tenfold steps. Each unit is a rung on a ladder, evenly spaced, rising and falling with no hidden gaps or traps. The gram, the litre, the meter, each belongs to a family where prefixes bestow order. Milli for 1,000th, centi for 100th, kilo for 1,000 times. Deca and deci, hecto and centi. These syllables are the musical notes of metric, each carrying its own weight, its own place in the scale. This is not how it once was. In the old patchwork of measurement, to convert from pounds to ounces, from furlongs to chains, from gallons to pints, was to step from one world into another, each governed by its own logic, its own history. But in metric, the rules are laid bare. 10 of this makes 1 of that. 100 of these become 1 of those. It is, in its way, a system that invites anyone, child or scholar, merchant or farmer, to participate. The decimal, that ancient invention of Indian mathematicians and later carried west by traders and translators, is the guiding principle, a single, unbroken thread. Yet the river, for all its surface calm, sometimes meets an obstacle, a fallen branch, a stubborn rock, a sudden narrowing of the banks. So too does the metric system, for all its clarity, encounter places where the flow becomes less smooth. Consider, for instance, the challenge of defining mass, not just in a laboratory, but in every context where weight and matter matter. The gram was conceived as the mass of a cubic centimeter of water at its densest, a definition that tied unit to substance, abstract to physical. Elegant in theory, this approach soon revealed its own difficulties. Water's density varies minutely with temperature and pressure. A cubic centimeter is not always easy to obtain or to measure perfectly. The dream of universality met the stubbornness of nature's variability. This yearning for absolute precision, this desire to pin the world down to a single, unchanging reference, would come to haunt the architects of measurement. For over a century, the kilogram itself was anchored not by a universal constant, but by a physical object, a platinum iridium cylinder stored under lock and glass in a vault near Paris. All other kilograms, everywhere in the world, were measured as echoes of this one silent artifact. But even metal, carefully guarded, is not immune to time. molecules drift. Mass is lost, imperceptibly, but lost all the same. The promise of permanence became a paradox. To be universal, a unit must be both everywhere and nowhere, tangible and yet untouched by the world. And so the story of metric is not only one of seamless conversion, but of the limits where seamlessness dissolves. The system invites us to believe in perfect order, but nature, with her subtle shifts and quantum rattlings, resists the net. There is a kind of beauty in these limits, and a kind of humility as well. The search for a flawless metric, a reference untouched by error, leads us to the threshold of what can be known or fixed. It is here at this threshold that we encounter the quiet presence of Kurt Gödel, a mathematician whose work would change forever how we think about systems, certainty, and the boundaries of knowledge. Gödel was not a man of rivers or fields, but of silent libraries and shadowed corridors, his mind moving in patterns as intricate as any labyrinth. In the early decades of the 20th century, as physicists and engineers pressed ever closer to absolute precision, Gödel's attention was elsewhere, on the foundations of mathematics itself. Could any system, no matter how elegantly constructed, be both complete and free of contradiction? Could every truth, if only we were clever enough, be captured within a single, perfect set of rules? His answer, delivered in a paper published in 1931, was quietly devastating. In any system rich enough to include arithmetic, there must exist truths that cannot be proven within the system itself. There will always be statements whose truth is beyond reach, whose certainty is forever just outside the lattice of logic. The metric system is not a system of logic, but it is a system, a constructed order subject to the same shadow of incompleteness. No matter how carefully one defines the kilogram or the meter, there will always remain the possibility of drift, of error, of the world refusing to be captured in full. This is not a flaw in the metric system alone, but a reflection of the deeper structure of reality. No measurement can be made without some uncertainty. No standard can escape the slow erosion of time. Even in the most controlled laboratory, the act of comparison, the weighing of a mass, the reading of a scale, introduces its own subtle noise. As night deepens along the river, a faint breeze stirs the reeds. Light from the far shore glimmers on the water, trembling with every ripple. You can almost imagine the scene in a late 19th century laboratory, where scientists struggled to reconcile the perfect order of metric with the messy, unpredictable world of experiment. The meter, defined as a fraction of the Earth's meridian, was soon found to be not quite as constant as hoped. The Earth bulges at the equator. Mountains and hollows distort the line. Later, the meter would be redefined in terms of wavelengths of light. Then, as the distance light travels in a specific fraction of a second, a definition linking the unit not to the shifting Earth, but to the constancy of the speed of light itself. Each of these transitions marks a moment where the system must adapt, where perfection is approached but never quite attained. The decimal structure remains, but the anchor points move ever deeper into the fabric of nature, seeking invariants that are truly universal. Here, the metric system becomes not just a tool of commerce and science, but a kind of ongoing negotiation with the universe, a dialogue between human aspiration and the world's irreducible complexity. Even the language of metric reflects this striving for universality. The prefixes, so neatly aligned in powers of 10, have grown over time to accommodate both the unimaginably small and the vast. Nano for a billionth, pico for a trillionth, mega for a million times, giga for a billion. These words, once the province of scientists and engineers, have slipped quietly into everyday speech. Gigabytes of data, nanoseconds of processing, megaton bombs. The ladder of metric now stretches far beyond what any single mind can easily picture. And yet, at each rung, the same principle holds, moving the decimal point, sliding along the scale. But no matter how fine the division or how grand the leap, the act of measurement remains bound by context. A nanometer is useful for describing atoms and molecules, but meaningless when measuring roads or rivers. A kilometer, so natural for a journey, is a clumsy unit for the breadth of a human hand. The metric system offers coherence, but the world demands judgment, a choice of scale, a sense of what matters in each circumstance. In literature, too, the dream of perfect order and its inevitable unravelling finds its echo. Long before Gödel, writers like Lewis Carroll played with the absurdities and contradictions that arise when systems are taken too literally. In Through the Looking Glass, Carroll imagines a world where logic and order are forever at odds with experience, where rules multiply until they become indistinguishable from nonsense. The Queen's insistence that jam tomorrow and jam yesterday, but never jam today, is a gentle parody of the limits of rule-making, a reminder that systems, no matter how elegant, must ultimately serve life, not the other way around. So we return for a moment to the riverbank, where the stones are both measure and measured. You might pick up a flat pebble and weigh it in your palm. Its mass could be stated in grams, its volume in cubic centimeters. You could, if so inclined, calculate its density, the mass divided by the volume, a value with its own metric unit, the kilogram per cubic meter. The metric system allows these transitions, these calculations, to flow like the river itself, but the pebble remains what it is, singular, textured, shaped by forces beyond the reach of any unit or prefix. In the classroom and the laboratory, the elegance of metric is taught as a kind of grammar, a set of rules for translating experience into number, for comparing one thing to another. Students learn to move the decimal, to substitute milli for centi, to see kilo as a thousandfold leap. These are real skills, hard-won and invaluable. But as one delves deeper, the picture becomes subtler, the boundaries less clear. The world resists total capture. Measurement, for all its rigour, is an art as well as a science. This is especially evident in the transition zones, the places where human experience and scientific abstraction meet. Consider temperature. The Celsius scale, another product of Enlightenment rationality, sets 0 as the freezing point of water, and 100 as the boiling point at standard atmospheric pressure. But standard pressure itself is an abstraction, rarely encountered outside a laboratory. The thermometer in your window measures not just the temperature, but the pressure, the humidity, the quirks of glass and mercury or digital sensor. Each reading is a negotiation, an interpretation of what the world is willing to reveal. Or think of the liter, a cube 10 centimeters on a side, a volume so precisely defined that it can be replicated in glassware or in the mind's eye. Yet in practice, a liter of milk is not quite the same as a liter of oil or a liter of air. Each substance brings its own properties, its own ways of filling the space, its own resistance to being perfectly defined. The beauty of the metric system, then, is not that it erases complexity, but that it gives us a language for engaging with it. The decimal ladder is a tool, a way of bringing order to a world that is, at root, always teetering on the edge of the unmeasurable. In the far distance, a train's horn echoes across the water, one long note fading into silence. The river continues on, indifferent to the units we impose. In the end, the elegance of metric lies not in its perfection, but in its adaptability. It is a system shaped by both aspiration and limitation, a product of minds who understood that universality is always a work in progress. As the sky fades from dusk to night, you might carry forward this quiet recognition that every system, no matter how seamless, has its edge. The decimal structure of metric is a kind of promise, but also an invitation, to see where pattern meets resistance, where the world's intricate texture quietly asserts itself. On a hilltop in the late morning, the world opens wide beneath the sky's pale clarity. We are far from riverbanks now, drawn upward to a place where the horizon seems to turn beneath us, and the land itself is a measured expanse. Here the air is sharp with anticipation, cool and thin, and the ground is scattered with the tools of an age that believed the world could be known, if only one dared to measure it. It is the year 1792, and two men stand in the shifting light of northern France, their figures outlined against the low sun. Pierre Méchain and Jean-Baptiste Delambre, each equipped with notebooks, telescopes, and the heavy, delicate bars of brass and platinum that serve as their measuring rods, are about to attempt something extraordinary. Their task is to fix, once and for all, the length of a meter, not by decree, but by the very shape of the earth itself. The meter, as an idea, was already defined. 1/10,000,000th of the distance from the North Pole to the equator, along a line of longitude that passes through Paris. But the world, for all its apparent simplicity, resists such easy reckoning. To measure this arc, Delambre and Méchain must triangulate their way from Dunkirk, near the chill grey of the Channel, southward to Barcelona, where the Mediterranean spills sunlight onto whitewashed walls. Their instruments are the finest their century can provide. Precision theodolites, iron rods for baselines, delicate optical devices to sight distant church spires and mountain peaks. Each triangle they build is a leap of faith, a calculation of angles and distances stitched together over hundreds of kilometers. Imagine them, day after day, in the wet mists of the north, or under the fierce Catalonian sun, carrying their rods and their doubts. There are days when the clouds close in, obscuring their targets, and nights spent recalculating errors by candlelight. At one point, Méchain, haunted by a small but stubborn discrepancy in his measurements near Barcelona, delays the project for months, obsessed with finding the cause. He is acutely aware that the weight of the new world, this metric world, will rest on the precision of his numbers. This is not just an act of science, but of hope and peril. Revolutionary France is in turmoil, and suspicion shadows every traveller. Delambre is arrested more than once, suspected of espionage as he lugs his strange apparatus from village to village. Yet the work continues. Little by little, with each surveyed triangle and every carefully recorded angle, the arc of the meridian is revealed. The meter that emerges from their ordeal is not a guess, but a distillation, a length born of the planet's own geometry, as measured by minds and hands determined to touch the infinite through the finite. Their survey, completed in 1799, remains one of the age's scientific epics. The errors, when they are finally tallied, are minuscule, a few 10,000ths of a meter, lost in the sheer ambition of the project. The new meter bar, forged and kept in Paris, is a physical memory of their journey, a rod of platinum shaped by the arc of the earth and by the resolve of those who dared to measure it. Long after Delambre and Méchain have faded into history, the meter remains, but the world around it grows restless. The urge to anchor the units of measurement in something unchanging does not abate. By the middle of the 19th century, the kilogram has already been defined, as we have seen, by a carefully crafted cylinder of platinum iridium hidden away in a climate-controlled vault. But these artifacts, for all their elegance, are vulnerable to time and circumstance. A single scratch, a speck of dust, a subtle chemical change in the air. So in 1879, in a refined laboratory not far from the heart of Paris, a new challenge begins. Here, under tall windows that filter the city's grey light, a small group of metrologists, craftsmen and scientists both, turn their attention to the creation of the international prototypes. They are surrounded by the quiet clink of glassware, the scent of polish and oil, and the hush of concentration. Their tools are simple in appearance, but require skill bordering on artistry. Fine balances that can detect a fraction of a milligram, lathes cut to tolerances measured in millionths of a meter, and chemical baths to purify their metals. The making of the international prototype kilogram is a labor of patience. The platinum and iridium are melted and cast, then slowly cooled to avoid internal stresses. The resulting ingot is turned and polished by hand until its surface is as mirror-like as the stillest pond. Every few passes of the cloth, the balance is checked against the reference weights. A stray fingerprint or a mote of dust can tip the scales. The finished cylinder, just 39 millimeters tall and 39 millimeters wide, emerges from its velvet-lined case like a jewel, yet it is defined not by beauty, but by sameness. It must match the reference, gram for gram, to serve as the anchor for all weights on Earth. Once crafted, the prototype is stored with ritual care. It lives beneath 3 bell jars, nested one inside the other, and is handled only with gloves. Every few decades it is removed and compared to its official copies, a solemn ceremony attended by international delegates where the fate of the world's commerce and science is weighed, literally, on a scale of unimaginable precision. And yet, over the centuries, it becomes clear that even platinum and iridium, so noble and unchanging, are not immune to the world's quiet persistence. The kilogram's mass drifts imperceptibly as atoms are lost or gathered from the air. The artifact, meant to be eternal, is revealed as merely human. As the 20th century advances, the search for permanence resumes, this time with new tools and new ambitions. The meter, once cut from the arc of the Earth, is now to be fixed by the deepest constant nature offers, the speed of light. In May of 1983, in a meeting room at the General Conference on Weights and Measures in Sèvres, a decision is made that will unmoor the meter from all terrestrial things. The new definition is as audacious as it is elegant. The meter will be the distance light travels in a vacuum in exactly 1,299,792,458th of a second. To make this real, a new kind of instrument is required. The old meter bars are retired, and in their place come lasers, tools that seem to hum with the future. At the Bureau International des Poids et Mesures, scientists align their apparatus with care. A stabilized helium-neon laser, its beam a perfect red line, is passed through an interferometer, where it is split and recombined. The resulting pattern of light and dark fringes is counted one by one as the beam traverses a known distance. Each fringe is a wave of light, less than a millionth of a meter wide, recorded with a click, a flash, a tally in a notebook. The precision is astonishing. Where Méchain and Delambre once stared across valleys and rooftops to fix their triangles, now the meter is written in the language of quantum mechanics and relativity. The speed of light, a constant of the cosmos, is measured with atomic clocks so stable they lose less than a second in millions of years. The meter, as it is now defined, is not a thing but a process, a dance of photons, a rhythm of the universe itself made manifest by human ingenuity. Each of these stories, the meridian arc, the platinum kilogram, the laser meter, is a testament not just to the urge to measure, but to the tools and minds that make measurement possible. The instruments themselves are as much a part of history as the numbers they produce. The theodolite, the precision balance, the laser interferometer. Each is a bridge between idea and reality, a device for translating the world's ambiguities into something definite, and behind every tool, a mind at work. Méchain's perfectionism, which drove him nearly to madness over 1/100th of a degree, the anonymous hands that polished the kilogram, trusting that their unseen labor would serve generations. The physicists of the late 20th century who trusted in the invariance of light rather than the stability of metal. The world is measured not just by rods and beams, but by the patience and doubt, the hope and resolve of those who wield them. The metric system, for all its abstraction, is born of sweat and fear and wonder. It is not an edict from above, but a conversation between nature and the human mind, replayed in every experiment and every recalibration. Each time a scientist checks a weight, sights a beam, or watches the interference fringes slide past, they participate in that long dialogue, a dialogue that stretches from the dusty fields of revolutionary France to the sterile quiet of modern laboratories. If you listen to the stories these tools tell, you hear not only the march toward precision, but the acknowledgement of uncertainty. The meter defined by the meridian was imperfect, but it was the best the world could do with the tools at hand. The kilogram's slow drift is not a failure, but a sign that matter itself is restless, alive to change. The laser meter, pegged to the speed of light, is as close to eternal as we can imagine, and yet it too is bound to the fallibility of clocks, the calibration of lasers, the subtle hands that keep the experiment running. What this means, quietly, is that the metric system is not a monument, but a living thing. It grows and adapts, not by erasing its past, but by building upon it. Each new definition is a layer, a refinement, an answer to a question first asked centuries before. The tools and minds of the metric revolution have not conquered ambiguity. They have learned to live with it, to measure and remeasure, to accept that precision is both a promise and a pursuit. The world measured by this system is both more certain and more mysterious than before. Every kilogram, every meter, every second is a story, a trace of human hope and error, a mark left by light, metal, and time. The metric system, for all its global reach, remains intimate. It begins and ends in the hands of those who dare to measure, to doubt, and to begin again. Tomorrow, perhaps, the tools will change once more. The kilogram, now defined not by metal, but by the Planck constant, a quantum of action measured in the tiny whirls of electrons, speaks of a new age where the very fabric of the universe is written in our units. But even as the tools become stranger, the impulse remains, to reach out from the known toward the unknown, to draw a line, to set a weight, to measure the world and our place within it. The legacy of the meter's arc and the kilogram's cylinder is not only in the numbers they fixed, but in the method they embodied. The willingness to build, to observe, to err, and to correct. The humility to recognize that every measure is provisional, every standard a compromise with the world's restlessness. Here, on the hillside where the horizon curves and the air sharpens, you might imagine a line drawn from the northernmost church spire to the southernmost mountain peak, a line both real and abstract, both a feat of human ingenuity and a concession to the earth's subtlety. Along that line, men and women have walked, measured, doubted, and dreamed. And so the story continues, one experiment at a time, one tool after another, each a quiet answer to the world's infinite variety. The metric system endures not because it is perfect, but because it is perpetually becoming, an unfinished measure, a standard always in motion. The next chapter will belong to those who measure the smallest and largest things, who seek constancy not in metal or stone, but in the unwavering rhythm of the universe itself. In a quiet room not far from the sea, the world slows. The air is cool and still, the faintest tang of salt drifting through an open window. A desk stands in the soft light, its surface almost bare, but for a single object, an ordinary kitchen scale, its digital numbers dark and silent, waiting. The room could be anywhere, Lisbon or Reykjavik, Buenos Aires or Hanoi, because the language of numbers it speaks is universal, a thread that winds unseen through kitchens and factories, hospitals and spacecraft. Here, as the evening hush deepens, we find ourselves in the gentle presence of measure itself, the quiet order that steadies the world. The story of the metric system, so carefully traced in the iron and platinum of earlier centuries, now unfolds in every ordinary space. A child pours milk into a glass, watching the line on the measuring jug rise to 200 milliliters, the digits printed in a neutral, unfussy type. In a hospital, a vial is filled for a vaccine, its volume exactly 1 cubic centimeter. On a distant construction site, a tape measure rattles out 0.5 meter of steel. The numbers are the same, whether spoken in Swedish, Swahili, or Mandarin, each a ripple from the same deep source. No matter where you are, a meter is a meter, a kilogram is a kilogram, a second is a second. In this way, the metric system is quietly radical. It dissolves borders not by force, but by gentle insistence, by the steady rhythm of agreement. At the root of this agreement is something both profound and practical. The meter and the kilogram, once anchored in precious bars and cylinders, now rest upon constants of nature, on the speed of light, on the unchanging Planck constant that links the mass of a particle to the energy of its vibration. Instead of objects that can be lost or change their weight with a speck of dust, we have turned to the universe's own invariance. Every laboratory, every home, every classroom holds the same reference, even if only by proxy. It is a kind of promise that the world is knowable, that we can share a common understanding. This promise did not come all at once, nor without argument. The metric system we know today is the result of centuries of debate, revision, and slow compromise. In the late 19th century, as the kilogram prototypes were cast and polished, nations sent their scientists to Paris to compare their own standards, sometimes finding discrepancies that had to be reconciled with care. The International Bureau of Weights and Measures became a diplomatic ground, a place where the lines between politics and science blurred. Over the years, dozens of countries, eventually almost every country, signed onto the treaty that created the system, the Meter Convention of 1875. Through this shared system, the world found something rare, a standard that belonged to everyone, yet favored no one. The units are not the legacy of a single king or culture. They are not inscribed with the name of a ruler, nor tied to the length of a monarch's arm or foot. Each unit is built from the ground up, rooted in the fabric of the world, and revised when our understanding deepens. When the kilogram was finally redefined, not by the heft of metal, but by the Planck constant in 2019, it was a moment of quiet celebration in laboratories from Ottawa to Johannesburg. Scientists everywhere could reproduce the standard, using instruments as precise as the universe allows, without needing to visit a guarded vault in France. Look more closely, and you see how this system shapes daily life. A baker in Morocco reads a recipe, 100 grams of flour, 50 grams of sugar. The same recipe, written in Vietnamese or Finnish, produces the same bread. An engineer in Nairobi designs an irrigation pump. Her calculations in liters and meters will work just as well if the pump is built in Jakarta or Lima. In medicine, where precision can be the difference between harm and healing, the shared language of milligrams, centimeters, and degrees, Celsius is a quiet safeguard. This unity is not only practical, it is also a gentle invitation to humility. The world is vast, cultures are many, and the ways we see and name things are wonderfully different. Yet here, in the act of measuring, we agree to yield, to let the shape of the earth, the speed of light, the pulse of atomic clocks set our terms. The metric system is not a flattening of diversity, but a kind of deep respect for the common ground beneath our feet. The order it brings is easy to miss because it is so unassuming. The numbers on a medicine bottle, the markings on a road sign, the labels on a bag of rice, each is a quiet reassurance that somewhere far away another person will find the same measure, the same certainty. In this way, the metric system is a scaffold for trust. When a spacecraft leaves Earth, every calculation, from the thrust of its engines to the timing of its signals, is built on standards so stable that even the vacuum of space cannot erode them. The meter, the second, the kilogram, These are the rails along which our ambitions travel. There is, however, a subtle beauty in the fact that even this system, so carefully wrought, is not absolute. For all its constancy, there remain puzzles at the edge of knowledge, places where the act of measuring meets the strange limits of the universe. The quantum world, for instance, resists our efforts to pin things down with perfect clarity. Werner Heisenberg showed almost a century ago that the more precisely you know the position of a particle, the less precisely you can know its momentum. This uncertainty is not a flaw in our instruments, but a feature of reality itself, woven into the mathematics of quantum physics. The Planck constant, which now defines the kilogram, is also the marker of this irreducible fuzziness. At the largest scales, too, measurement encounters mystery. In the heart of a black hole, where gravity crushes matter into a single dense point, the very fabric of space and time is distorted beyond our current power to describe. For decades, physicists have puzzled over a quiet paradox. When something falls into a black hole, what happens to the information it contains? Stephen Hawking, who first understood that black holes can emit a faint glow, now called Hawking radiation, opened the door to a new kind of measurement problem. If the black hole evaporates, is the information truly lost, or does it escape in some subtle, scrambled form? This is not a question of mere curiosity, but a test of the deepest principles of physics, of whether the universe ultimately preserves or forgets its own history. Such puzzles remind us that every system of measure, no matter how refined, is a bridge between what we know and what we do not. The metric system is not a final answer, but a tool, shaped by our best understanding and always open to revision. Its constants are chosen not for their perfection, but for their ability to knit together the old and new, the precise and the possible. In this, the metric system is a sign of hope, a recognition that, even in a universe whose edges are lost to us, we can build islands of certainty. So, as the sky darkens outside the window and the room settles into quiet, the kitchen scale waits, ready to translate the world into numbers. The same numbers everywhere. A gentle sense of order drifts through the house. The faucet in the kitchen drips once, 1 milliliter, then another. The refrigerator hums, coils warming 1 measured degree at a time. On a shelf, a glass measuring cup catches a stripe of moonlight. Its lines are clear and silent. 200 milliliters, 1 cup and a little more. Down the hall, a school backpack leans against a chair. Inside, a pencil case holds a short plastic ruler, 10 centimeters, marked in careful blue. The clock on the wall ticks, each second exactly the same as the one before. Far away, a train rolls past, its distance measured in kilometers, its speed in meters per second. Stillness gathers in the corners. The numbers remain. Order everywhere. Quiet, precise. The room is calm. The world is measured. All is steady here. The world settled on meters and kilograms because they fit the way we move and measure. A meter is the length of a pendulum swing. A kilogram is the weight of a liter of water. Let that quiet.